So in the last video, we looked at the equation of state and how we can use it to describe the relationships between different variables. In this video, we're going to look at how we can actually apply the equation of state to deal with and do calculations in specific scenarios. So we're going to deal with scenarios with fixed volume, pressure, temperature, but all of them are what we're going to be called sealed systems. So the number of molecules, or the mass effectively, of the gas will stay the same throughout. So let's get started. So the first scenario we're going to look at is if we've got a sealed fixed volume container. So just one thing to draw your attention to. So we've got the equation PV equals NKT. So the K, the constant, is known as the Boltzmann constant, and it's named after a German scientist, Boltzmann. And it has a specific value of 1.38 times 10 to the minus 23. So it's a really, really small number. But when we're dealing with these equations, we very rarely actually have to use what the constant is, and I'll show you why. So we've got a sealed container, so we know that N is going to be staying the same because gas particles can't escape or arrive into the system. So if we have a constant volume, what I'm going to do is exactly like I did in the last video. I'm going to take volume to the other side and replace the NK and volume with a constant I've called C subscript V. So what then I can do is, if I change either the pressure or temperature, that will allow me to work out what happens to the other variable. So essentially what we can do is, if we look slightly to the right, you can see I've divided both sides by the temperature to make the constant the subject, because this constant will have the same value regardless of the pressure or temperature. So the form we often see that in is P1 over T1, so the pressure to start with and the temperature to start with must be equal to the pressure afterwards and the temperature afterwards. So essentially this would allow us to look at the relationship between temperature and pressure if volume is constant and it's a sealed container. So let's actually use this for a question. So this equation that we're using is often called the pressure law. It does have another name as well, but it's most commonly known as the pressure law. So if we've got a fixed volume sealed container of gas at 20 degrees and initially 100 kilopascals, and it's heated to 100 degrees centigrade, so then what we want to do is work out what the final pressure was. So if we remember, in the gas equation, our temperatures need to be in Kelvin. So that's the first thing I would do, is convert temperatures to Kelvin and convert the pressure into just pascals, because that's the standard unit of pressure. Then I bring out the pressure law that we derived in the last part and rearrange it to make the final pressure the subject, because that's what we want to calculate. Now we're in a position to substitute our numbers in, and that will allow us to calculate what the final pressure is. So the thing to spot at this point is, as long as we've got our temperatures in Kelvin there, you can see our 2 units of Kelvin are going to cancel out. So it wouldn't actually matter what unit of pressure we put in. So if we put the pressure in kilopascals, we would get the pressure out in kilopascals as well. So we didn't actually need to convert the kilopascals into pascals, but it's a good habit to be in anyway. But we must convert temperature into Kelvin, otherwise it changes the calculation there. So that's how we use for a fixed volume sealed container. Let's have a look at a sealed but fixed pressure container. So the first thing is to explain how we achieve a fixed pressure. So what we have is a container that is able to change its volume to equalize the pressure. So a syringe might be an example, a piston might be another example of this. So if we've got constant pressure, I'm going to make volume the subject in the equation, which we can see on the left-hand side. And then what I'm going to do is I'm going to make NK over pressure equal to a constant. And that's what we've seen there. And that's like we saw in the previous video. So then I'm going to make the constant the subject of the equation. So V over T is equal to the constant, which means V1 over T1 is equal to V2 over T2, because they're both equal to the same constant. So we can look at the relationship between the temperature and the volume of the gas. This relationship is often known as Charles's law, again named after a famous scientist, like a lot of them are. So we've got a sealed fixed pressure container that's initially at 20 Kelvin and it goes to 150 Kelvin. And we want to know the initial volume if the final volume is 20 centimeters cubed. So essentially, these are the variables that we've been given. So first, let's get our expression of Charles's law and rearrange to make the initial volume the subject, because that's what we want. Then we can put our values in. So you'll notice here that it doesn't matter what unit we put the volume in, it just means that we get the volume out in centimeters cubed if we put the volume in centimeters cubed. But again, we must put our temperatures in Kelvin for this to work. So we can see that before we heated it, our volume is much smaller than after we heated it, which is what we should expect from the graphs we drew in the last video. So that's that scenario. Let's look at a sealed constant temperature system now. So if temperature is constant, what I'm going to do is I'm going to turn the NKT all into one constant, and then I'm going to make that constant the subject of the, on the bottom left, we've got the expression we had from the previous video. I'm just going to make the constant the subject though, to give us our expression that we've got before. So pressure times volume initially must be equal to the pressure times volume afterwards. So we can look at the effect if we change the volume of our system, what effect will that have on the pressure? So this is often known as Boyle's law. And what we can do is let's have a look at a scenario we can use it. So we've got a gas being compressed from 0.40 meters cubed to 0.20 meters cubed, and it's left for a long period of time, and then the pressure is measured. We want to know what the final pressure we'd get is if we know the initial pressure. So these are our values, and again we want to know the final pressure, so I make that the subject of the equation there. So we can put our values in. So what we can see there is we've ended up with double the pressure we had to start with, and you can see what we did is we halved the volume and we've therefore doubled the pressure if temperature stays the same. So that is an expression of an inversely proportional relationship. If you halve one, you should double the other. So that makes sense to us. So the reason it tells you it's left for a long period of time is because that means the temperature is going to return to what it was initially. Because if it gets hotter, it's going to send thermal energy out to the surroundings and become the same temperature again. So that's what that piece of information tells you. It tells you it's a constant temperature process. Okay, so to the last one. So we're not going to keep either volume, pressure or temperature constant, but we're still going to have a sealed system. And this is the most complicated this modeling gets. So what we can do is we can remove t to the other side, so divide both sides by t, and we make n and k just equal to a constant because n is a fixed value. So what that means is that P1 V1 over T1 is equal to P2 V2 over T2. And this is the most complex modelling we're going to deal with when modelling gases. So we can have a look at how all three of these change with respect to each other. So to give you a scenario, so if we have a container of gas and we halve its volume and quadruple its temperature or times by 4, what effect does that have on the pressure? So first of all, we can get our expressions there. So we said the volume is halved, so we know the initial volume is double the final volume. And we said the temperature is quadrupled, so the final temperature is 4 times the initial temperature. So we've got our statement that the PV over T is equal to each other. We want to find the final pressure, so I make P2 the subject. And then all I'm going to do is I'm going to make some substitutions. So T2 is equal to 4T1, so you can see that's gone in there. And V2 is equal to V1 over 2, so you can see that's gone into there. The T1s are going to cancel, the V1s are going to cancel, and that just gets left as 8 times P1. So the pressure will be multiplied by 8. That's how we would describe the change in pressure of the system. Okay, so those are our 4 scenarios we'd need to be able to deal with our gas laws, and it's how we can actually deal with those. So do have a look through and think how you would approach each of these scenarios and see if you can, because if you can't, you need to go back and go through those again. If you have any questions, feel free to ask me and comment on this video and I'll try and get back to you. But thank you very much for taking the time to watch.